Yeah, I think it's a good. So basically, we went through the brains. Fine. I think a good time to now move to the superstring. And if there are one or two calculations we forgot to do, we will do it in the context of doing the calculation in the superstring. Okay. So this semester, let's focus our attention on the superstring. Okay. So my plan for the next few classes will be to give you some to start out by giving you some intuitive feel for what goes on with the superstring. Okay. So the first thing I was planning to do was to go through the supergravity actions for 11-dimensional supergravity, type 2a supergravity, type 2b supergravity, and the heterotic string. And then to go back to our understanding of vertex operators and try to see how the massless sector, try to see in detail how the vertex operators that we looked at in the massless sector corresponds in detail to these the fields that we see in supergravity, and also to understand this correspondence well. You'll see that the vertex operators, in the case of Ramon fields, correspond to field strengths rather than potentials and so on. All those things we need to carefully take a look at. Okay. Okay. After that, we'll see. Sorry. Hello. Okay. Yeah. So the things we want to talk about are d-branes in the superstring. We want to talk about them both from the supergravity point of view as well as from the world sheet point of view, and to tie the two things together. We want to talk about orbifolds and orientifolds in the superstring, again both from supergravity point of view and from d-brane point of view, and tie the two of them together. So roughly the material we want to cover is in the first few chapters of Pulchinski's textbook, up to chapter 14. I was also thinking we could go through the parts on compactification of Green-Schwarz and Calabi-Yau compactifications. Yeah, so we will discuss anomalies and all that good stuff. Okay, so let's start. So in today's lecture is just a rough warm up on supergravity. So we'll start by looking at 11D supergravity. Now, why 11-dimensional supergravity? Well, there is this very simple argument that tells you that you cannot have a theory of supergravity in higher than 11 dimensions. Okay, I'm going to quickly review that argument for you. Okay, so the argument is basically one of number of supercharges. So more precisely, the argument goes, you cannot have a theory of supergravity with more than 32 supercharges. Supergravity in flat space with more than 32 supercharges. Okay, and the argument is a very simple one, and I'm going to quickly review it for you. As you might remember, have all of you people looked at this paper by Strathedy on representations of Poincare supersymmetry? Okay, this is essential reading. This is a paper. I'm not going to go through it in class. It will take us too long. But okay, I'm going to give you like a 5-minute outline of what he does here, just enough to get to what we want. But I strongly recommend you read this paper, and even more strongly recommend you photocopy it and keep it with you, because it's the kind of paper you keep looking up. Okay, it's got lots of tables, very useful tables. Okay, so what's the idea? The idea is that you've got a theory. Suppose you've got a theory with some amount of supersymmetry. You want to understand what kind of particle content the theory can have. So the analysis that Strathedy does goes very much along the line of the analysis of little groups for the Lorentz group. Let me remind you how that analysis went. Okay, the analysis of the little group analysis goes like this. It's different for massive and massless particles. Yeah. Okay, for a massive particle in d space-time dimensions, you boost, first you remember that all, the Lorentz group has translations. Translations mutually commute with each other, and we look for a basis of states in which translations are diagonal. Okay. What we're looking for is momentum basis for particles. So our basis of states has some other indices that we're unsure about, but also k mu. Now, all k mu's are equivalent. All k mu, so we're looking for a basis of states for a particle of a certain mass. So k squared is equal to m squared, and all k squared equal to m squared are equivalent, because you can go from one to the other by a Lorentz transformation. So we might as well boost so that we're in the rest frame. Okay? So we've got some other indices and we've got k0. We can do this for every k mu because they're all symmetry related. So might as well do it once and for all, and then we're not getting anything new. Okay. Now,
so this is only for massive particles.
So far only for massive particles. There'll be a small modification of this for massless particles. Okay. Now we've understood how, so the Lorentz group includes m mu nu and p mu's. We've already in our basis seen how p mu acts, because p mu acts as k mu in this basis. We're working on a basis in which p mu is diagonal. Now, what about m mu nu? Okay. You see, some of the m's take you from one k to another k. But some m's stabilize k. So the analysis of little groups goes first this way. First you try to find the representation of those m's that stabilize the k. And then you try to deduce the representations of the m's that do not stabilize the k. There's no, that second representation is completely determined. Okay? All the data in the representation goes in the analysis of the m's that stabilize the k. Okay? So which are the m's that stabilize k? Well, clearly mij, where ij are spatial indices. So these are generators of SO d minus 1. Okay, so these other indices here are indices of a representation of SO d minus 1. If you want one particle, it's got some irreducible representation. Okay, and then the little group analysis tells you that, so basically to specify a state in a given value of k, you need to specify a representation of, you need to specify which representation of SO1 d minus 1 you're dealing with. That tells you which particle you're looking at. And then you need to specify some representation index in that representation. And then the little group analysis tells you how to implement the M0i's, how the boosts are automatically implemented in this representation. I'm not going to go through that. We don't need it for what we're going to do. Okay? The key thing here was that the particle was specified by specifying some representation of SO d minus 1. And then, of course, in its rest frame. Then there's a similar thing in every frame, and then there's a story of how boosts act. Okay, that's great. Now, we are interested in how this should be generalized to a theory of supersymmetry. Okay. Now, as you guys remember, supersymmetry has some Q operators with some algebra, right? Schematically, this is Q is equal to P. The analysis I'm going to give you is slightly modified if you have central charges. I'm going to tell you about the analysis without the central charges for now. Okay? And then we have MQ is equal to the spinor representation of M acting on Q, because Q's are spinors. M rotates Q like a spinor will. So this is a spinor representation of SOD acting on Q's. And of course then the rest. Right, Q commutes with P. And then the Lorentz generators. PP is 0, MP is vector representation of M acting on P. I'm not going to write those down. Okay? So once again, if you want to find the particles that can appear in a supersymmetric theory with a given supersymmetry algebra, once again you adopt the procedure of the little group. So you go to a basis where momentum is diagonal. Okay, so once again now what you're in is some basis in which your momentum operator here is p mu is equal to k mu. It's just something. And now you have to represent the rest of the algebra. Okay, the rest of the algebra consists of what? It consists of the q's, because the q's commute with p, so they don't move p away from your fixed frame, and the rest of the stabilized algebra, the q's, and it consists of the mij's as before. Okay, so what you want is the representation of mij. So now mij of course has its own algebra. Mij commutes with the q's as mij commutes with q's, like we've written down, some spinor representation. And what's important is what about the q's? So the q went to p. P is purely p0. Okay, so a little less schematically, you'll have a q alpha, q beta will be some gamma 0 alpha beta p0. Roughly, exact details depend on different dimensions, but roughly this is a schematic form of this commutation relation. Now what you see here is that what we have is that this object here is like a Clifford algebra.
This is P0 because it is a central.
Because we're in the rest frame. Okay, now this is something like some sort of Clifford algebra, right, where you have fermionic objects such that pairs of fermionic objects anti-commute to something particular. Okay, so if the total number of supersymmetries was n, then what will the dimensionality of this representation be? Well, if the total number of supersymmetries was n, let's say the total number of supersymmetries is 2n, let's say. Okay, then you would take these two q's, divide them into annihilation q's and creation q's.
2 to the 2 n.
So you would have 2 to the power n. Your representation will be 2 to the power n dimensional. Is this clear? No? See, suppose you had a Clifford algebra. Gamma I, gamma j is equal to delta ij. Okay, now suppose in this Clifford algebra you had 2n dimensions. What is the dimensionality of the spinors? How do you figure this out? Well, you see, you break this up into gamma plus and gamma minus to the annihilation and creation operators, fermionic annihilation and creation operators. You look at a vacuum which is annihilated by all the annihilation operators, and then it could be that or that times creation, but you could have one of these in each of the two planes. Okay, so the number of two planes was n, so you would have a spinor whose dimensionality was 2 to the power n. Actually, you know, the same is true even if the number of supersymmetries is 2n plus 1, right, because you get the gamma 5. That additional thing is represented as gamma 5, the analog of gamma 5 in that dimension. You know, spinors of SOD minus D plus 2D, S of 2m plus 1 and S of 2m have the same number of, have the basic spinor has the same number of components, and then now you can break up this spinor of SO2n into chiral and antichiral. Okay, all that we can do. Okay, but you see here, what we get is a representation of this algebra, and that representation of the algebra gives you the whole spinor, not chiral or antichiral. It just generates, the Clifford algebra contains these many components, as we've explained. Is this clear? So The same thing, you have to go through the details. This paper has all the details. You have to get the indices right and so on. But the same thing goes through here, and you produce representations. Okay, you produce spinorial representations with 2 to the power n components. Now, the full representation that you have to look at is given by k mu. Then, these 2 to the power n components. And there's one more slightly tricky thing here, which actually will play no role in what I'm going to say, but let me tell you about it.
The central charge.
No. Central. Let's say there are no central charge. Okay. This, once again, you might think that what you have to do is to specify a representation of SOD d minus 1, because you still have to represent the m's. The full little group, the full stabilizing group is SOD minus 1 times the spinors. But there is a problem here, because SOD minus 1 doesn't commute with the spinors. So it's not just a direct product of 2 things. The way you do it is to produce, you see, using spinors, you can construct SOD minus 1 generators such that the spinors will transform under this SOD minus 1, the way spinors should transform. This is the famous construction, right? The famous construction which tells you that in gamma matrix language, that m mu nu is equal to gamma mu gamma nu by 4. Gammas were our q's. So, by doing it appropriately, you can construct a generator of SOD minus 1 under which spinors transform the way they do. But under M, they also transform that way. So, under M minus this constructed generator, the spinors are now neutral. Now, that combined thing is some N, which also obeys the commutation relations of SOD minus 1. So, the thing that is really like you specify the state content that you get from here, plus an arbitrary representation of n, which is equal to m minus q gamma q, q commutator q, roughly speaking. You understand? This is an SOD minus 1 that commutes with the q's. I'm not going through this in detail. This would take a whole lecture. Okay, I'm going to ask you to go read this up. I'm just giving you the basic idea, just enough so that you can understand the counting. This is you're constructing a new SOD minus 1 set of generators which commute with Q. The fact that you could do it is that because you have 2 different SOD minus 1 generators in the game, both of which act in the same way on Q. The M's and the one you construct out of Q's. So you just subtract them. Okay? Right? So you get the general representation is specified by representation of n, a representation of the spinor, and k mu. Now, you are usually interested not in how n acts on a particle basis, because n is something in your head. You are interested in how momentum acts on it, because that tells you what the physical spin is. Okay? But now what do we have? This is an example of Clebsch-Gordon. Because n is like addition of angular momentum. It's j plus j or j minus j, which makes very little difference. Okay? And what you have is, we know what the representations in m spaces. We know what the representation in q spaces. And you want to find the representation in n, which is m, or m, which is n plus qq. So what we've got is a tensor product Hilbert space, and we want the transformation of the net angular momentum. So this is given by Clebsch-Gordon. So you take this spinor representation here, see what representations of SOD minus 1 it decomposes into. Clebsch-Gordon with the non-trivial representation of SOD minus 1 you had here. That gives you sum of representations. And that sum of representations is the representations in which your set of particles will transform. And that set of particles is your supermultiplet. Is this clear? Okay, of course, as you can see, I've not gone through it in any detail, but is the idea clear? Okay.
Yeah.
Now, always if you take Clebsch-Gordon of something with something else, you get bigger sets of representations than if you just had the Clebsch-Gordon of that same thing with identity. So the smallest representations you will get are those in which the n representation is chosen to be trivial.
What representation you said supermultiplet? It is the Clebsch-Gordon of this M and
You choose whatever n representation you chose,
yes.
then Clebsch-Gordon that with whatever you take the spinor space and decompose that
Yes, yes.
into representations of SOD minus 1. It's not quite what you might think, because when these were vectors, you got spinors. But these are not vectors, these are spinors. So you'll get some other representation. You have to do it a bit carefully. Decomposing these into representations of SOD minus 1 is a little work. Okay, for instance, in SO8, if this was SO8, it would be you get by triality. Other dimensions, you have to work it out. Okay, but the idea is clear, right? I'm not trying to go through the particulars. Okay, so you get some by that Clifford algebra that decomposes into some representations of SOD d minus 1. How do you figure that out, by the way? Well, you know how to construct the generators of SOD minus 1. From that, you can figure it out. You know the Hilbert space, you know the generators, because it's that Q commutator Q kind of generator. Okay? So you've got some representations of SOD minus 1 here. That's just fixed once and for all. And then there's a choice. Any other representation of SOD minus 1. That's up to you. That was like the choice that we had in the little group analysis. Right? In ordinary little group analysis, that choice is what you see is what you get. That choice was the representation in which the particle transformed. That's not the same here, because we've got two SOD minus 1s. Right? One is something that comes out of quantizing the spinors, and one is your choice. And as we've seen from here, the actual physical M is the n that you chose plus QQ. So this is like addition of angular momentum. Okay? And so the representations you get are in the Clebsch-Gordon tensor product, whatever you get from tensor producting this representation, this fixed representation, with this chosen representation. Is this clear? Okay, fantastic. Now, as I was saying, you had a choice in representation here. That was like the choice we made when doing little group analysis. Now, the simplest set of particles you'll get clearly if you choose this to be identity. If you made that choice for Lorentz cube, you got the scalar, which is clearly the simplest thing you can do. But here, even when you make the simplest choice, you won't get the scalar. You won't get only the scalar. Because you'll always have what comes from here. So you'll always have, and these things will not be irreducible. There will be bunches of representations. And if you put non-trivial representations here, you'll get even less irreducible things. Each representation is a particle. Right? A representation, what is a particle? The particle is how it transforms under the SOD minus 1. That stabilizes. That gives you the spin of the particle. So the set of distinct SOD minus 1 representations you get is a set of different distinct particles. They all group together into one multiplet of supersymmetry. And this is what a supermultiplet is. Okay, it's a very simple group theoretic construct. I strongly recommend reading this paper. Okay? Great. So, we're good. We're good. Now, a thing you could ask is, in the simplest representation, okay, in the simplest representation, okay, how many states? Okay, yeah. First, let me ask this question. Suppose I had 2n such Okay, let me first tell you about the massless case, and then ask the question, because that's where we're really asking. So let me just work it out. Fine. So far we worked with the massive case. Now we want to go to the massless case. What is the main difference between massive and massless? The main difference is that you cannot take a massive massless vector and rotate it so that it has only p0. Because if you could, then it would be massive. Okay? You do the next best thing. You do rotate it to p plus, which is, a vector which is 1, 1, 0, 0, 0. Note that the coefficient behind this 1, 1 is completely meaningless, because you can boost it away. So you can always rotate it to some 1, 1. Okay? So now this analysis gives you this is equal. So first thing, of course, is that the non-trivial part of this little group, the stabilizer group, is SOD minus 2. So that's, of course, the first difference. And we saw that when we looked at Lorentz group. Massless particles are labeled by representations of SOD minus 2. It's a well-known thing. Okay? Now, what are we going to do with the, how does the spinor analysis change? Okay? The basic structure of the analysis goes through completely.
Something else remaining also, right? I can just do that, like these close to components.
There is something else remaining, but then in the usual analysis, you show that that is always trivially represented. Right. So the non-trivial part of this is always SOD minus 2. You're absolutely right. There's another part.
Yeah.
Okay. But that is there are the standard arguments that tell you that there's no non-trivial representation. All those are infinite dimensional or something like that. There's some standard argument. Okay. Okay. So the thing that is interesting, that is represented in a finite way, is this SOD minus 2. That's probably non-compact, that part, because it involves some boosting, right? Right. So, okay, so we've got this SOD minus 2, and we go through the same thing. Now, the main difference is this. You have QQ is equal to like gamma plus P plus, or gamma plus 1 if you want. We chose P plus equals 1, but I'll just keep it P plus. Okay, only P plus is turned on. No P minus, no, and no Pi's. P plus is P0 plus P1, let's say, and P minus is P0 minus P1. Okay. Now you might think that that the analysis is completely unchanged, but there's actually one very important difference. And the one very important difference is that, I told you here that this is sort of like a Clifford algebra. But it's very important for it to be like a Clifford algebra that you can diagonalize this action of Q's and get something non-zero on the other side. So in a Clifford algebra, you could choose Q's in pairs such that Q1 with Q2 is something. Q3 with Q4 is something. Now, in the standard way of doing the Clifford algebra, these somethings are the same. But if they want, you could scale the Q's. It doesn't matter what that something is, but it's very important that you can choose a basis such that these two things come about in pairs. This is sort of like, some sort of matrix involved here. That this matrix can be put in the form minus 1 minus 1, 1 minus 1, block diagonal in this form. But it turns out that when you analyze this relationship, because this is P plus rather than P0, what happens is that in this matrix, half of this is the part that is sort of with plus indices is block diagonal. But the part that is with minus indices is just 0. So of these supersymmetries, half of them group into a Clifford algebra. Okay? And the other half implement commutation relations which Q commutator Q is 0. The only representation of that is that Q is 0. It's like a Clifford algebra with 0 on the right hand side. The only unitary, non-trivial unitary representations of this thing is just 0. Okay? So half of these spinors are just inactive. It's the other half that act. Now this is a very important point. Okay? So now, if we're dealing with massless particles, and I'll stick to that because that's what we're dealing with in studying supergravity. If we've got a theory with 2n if we've got a theory with 4n supersymmetries, then effectively it's like having 2n oscillators. And so we will get a 2 to the power n dimensional space. So super Partic multiplet, the simplest super multiplet, will have 2 to the power n states. These states could be various spins of the same particle, or they could be different particles. The total number of states, counting all spin components as different, will add up to 2 to the power n. Is this clear? Okay.
Different spins of the same particle.
Meaning, so suppose you had a vector particle of SOD minus 2, that will count as d minus 2 components. The full Hilbert space is 2 to the power n dimensional. It is split up in sub-representation plus some other representation plus some other representation. The sum of the dimensionalities of those representations is 2 to the power n. Right? It's the total space, the total dimension of the Hilbert space, which then breaks up into, you can then take these states and break them up into representations of SOD minus 2. But that's the full dimensionality of that space. And non-trivial representations themselves carry dimension. This is not the number of particles. Right? Okay. Excellent. Now there's something even more important, which goes this way. Okay. By one can always do the following. One can always choose any particular two-plane. Okay. And
This number don't depend on dimension.
what?
This number don't depend on dimension.
It depends on the number of supersymmetries. Now the number of supersymmetries will have a minimum associated with dimension, because supersymmetries themselves transform in spinors of the dimensionality. We'll come to that in a moment. Okay? But I'm presenting it in a way so that it's universal, just depending on the number of supersymmetries.
No, I'm saying that you said these are sum over number of components of,
Yes.
let's say d minus 2 and the second term.
Yes.
Tensor.
Yes. So the particular particle content, no. The total number of states will always be 2 to the power n. How that is distributed between which particles and how many components in each particle will depend on dimension.
Will depend. I mean, I'm saying that is cancelling out.
Yes,
this
the
extra.
total number will always be 2 to the power n by construction, right? You've got a 2 to the power n dimension space. How it's distributed among representations is a very dimension dependent question. Clear? Okay, excellent. So now let's keep going. Now, when you look at this, if you actually make your Hilbert space of particles, you can choose, it turns out you can choose the following. You can always take a particular two-plane, let's say the 1-2 plane. You can always choose your annihilation operators to have minus spin in the 1-2 plane, and the creation operators to have plus spin in the 1-2 plane. Okay, so let's make that choice in what follows. So this is gamma minus gamma plus. Fine. In fact, it's automatic. You can make it. There is a basis choice. It's sort of automatic when you get the delta ij's. You see, because delta ij is spin neutral. So whatever comes here and there has to have cancelling SO2 spins. So if they have definite spin quantum numbers under SO, then if this is gamma minus, this will always be gamma plus. In fact, it's basically automatic. Okay? So now, that in the commutation relations, we've got gamma minus, anti-commutation, we've got gamma minus, gamma plus, and various other indices, because we don't have just one SO2, we have a whole SOD minus 2. I'm keeping track of one of them. Okay? This is equal to something. Now, what you do is it's your choice which is creation, which is annihilation. As always with fermionic oscillators. Complete symmetry between them. Let's just choose by convention that this guy is the annihilation and this guy is the creation. Which means that the vacuum state of your spinor construction will be the lowest spin state. And then you can raise the spin by acting on that vacuum state by gamma plus. Okay? So, what did we have? The total number of creation operators. Okay? The total number of creation operators was n. Because we had 2n active spinners. We broke them up into annihilation and creation. And there were n particles. There were n creation operators. Each of the creation operators carries spin plus. Plus is spin half. So, the difference between the largest spin and the smallest spin in your in your whole supermultiplet, keeping track just of spins under this 1 and 2 plane, the difference between the largest spin, sorry, hello, teaching, yeah, okay. So the difference between the largest spin and the smallest spin is n by 2.
No, n by 2 is plus n by 2 is the largest possible spin because gamma plus has it raises the spin by half.
No, but in our case, the spinner, the thing that played the role for the spin, yeah, exactly, were the Q's which carry spin half.
Yes.
So the total amount of raising that you do is n times half.
Oh, right. Oh, sorry. Q minus annihilates.
That's right.
Yeah. So n by 2.
So S diff is equal to n by 2. Now, if you land on some spectrum which is, has CPT symmetry in it, there will be, which you always will, there'll be a symmetry between the plus and the minus spins. Okay? So if your largest, so let's say that we're almost at the end of this counting. I'm sorry it's going on. Suppose the largest spin in your problem was S. Then S minus minus S. So 2S has to be at least, has to be greater than or equal to. Okay? This n by 2. So so S has to be greater than or equal to n by 4. In fact, in this minimum representation, it's actually always equal to. The greater than happens when you start tensoring with these other non-trivial n things. But anyway, all we really need is this greater. Now we're finally at the point where I can make the physics point I wanted to make. You see, suppose I want to have a multiplet of massless particles where S is no larger than 2. Because we don't know how to make sense of theories with massless particles with S greater than 2. It's very interesting why we don't know that. It's a long and interesting story, but I won't get into that. You've probably all heard this, right? That theories of massless particles with spins higher than 2, we don't know how to make sense of. Okay. Since we don't know how to make sense of them, there are also claimed theorems that they don't exist, at least classically. We'll avoid them. So we want by supergravity theory, what I mean is a theory which has supersymmetry and gravitons, but no particles, no massless particles with spins greater than 2. That's what I mean by supergravity theory. Therefore, what is the largest n? 2 is this inequality. I'm just making this an equality. Okay. Yeah, n can be smaller than, right? That's right. So n has to be less than or equal to 8. Now a total number of supersymmetries was taken to be 4n.
32 real supercharges.
Yes. So number of SUSIs is less than equal to 32.
Is this theorem called Weinberg-Witten theorem?
Yes.
I'm just asking.
You're asking whether that is the thing that establishes that you cannot have massless particles of spins greater than 2. Yes, that probably establishes it. Probably it's probably right. That's a very fancy thing. Okay, but you can just ask more pedestrianly. Can you construct a Lagrangian? Write down a Lagrangian which is interacting and doesn't have negative kinetic terms for a particle spin less than 2. There are theorems that you cannot do this. If you just try, you'll see where the trouble is. Okay, it's just Weinberg-Witten theorem is probably a very clean version of this statement. But just at the classical level, the miracles that happen that allow you to make Einstein Lagrangian. Let us remember, we could make a Maxwell Lagrangian by choosing gauge invariance, and it was very simple, linear theory. We could make an Einstein Lagrangian by choosing a different kind of gauge invariance. But that gauge invariance is very complicated because it was forced to be a nonlinear gauge invariance. And that very, very tightly constrains the theory. You try to do the same thing with more than 3 indices, and it's so constraining that it doesn't work. There's no solution.
What about these high spin theories?
Don't exist in flat space. Yeah, you can write them down. They can write them down at the free level.
Yeah.
At free linearized level, no problem. Okay, but there are theorems, right, that you cannot construct a gauge invariant set of equations of motion in flat space. It is possible to do in the ADS space.
Yes.
Vasiliev.
This is this huge accomplishment by Vasiliev, but it was only possible if you took all. You can't do it for just spin 3.
Yeah.
You need spin 0 and spin.
It's been infinite hours.
Infinite hour spins, all of them linked with some crazy gauge invariance. And now we understand that the reason we could do that is because there exist free field theories, right? These are the duals to free field theories.
Yeah.
So in ADS, it's a different story, but we're in flat space.
Yeah, I get it.
Yeah, we're doing Poincare supersymmetry. Okay, excellent. Excellent. So, we cannot have more than 32 supercharges in a flat space theory, where at least 32 linearly realized supersymmetries. Some of the supersymmetries are there, but realized in some non-linear manner, broken by the vacuum. No statement about that. The 32 unbroken supersymmetries in flat space vacuum cannot be realized unless you're willing to pay the price of getting particles of massless particles with high spin. Okay. Now, before we turn to making the conclusion from this, can somebody tell me, quantum field theories can be thought of as theories whose massless particle content does not include spins greater than 1. The only way we know how to make sense of spin 3 half massless particles is in the context of supersymmetry. So that's linked to
Supergravity.
Supergravity, exactly. Exactly,
Yeah.
supergravity. Linked to spin 2.
Yeah.
We don't know how to go beyond spin 1 without involving gravity. Okay. So let's say that more or less by fiat, we'll say a quantum field theory, we're making some sort of massless quantum field theory. Its particle content should not have spins greater than 1. With the same analysis, can somebody tell me what is the largest number of supersymmetries you're allowed in a quantum field theory?
16.
16, exactly. Because this S will just be replaced by 1.
Yeah.
So you will get n is less than or equal to 4, that's what you were saying, but then the total number of supersymmetries was 4n. So number of supersymmetries for Sugra is less than or equal to 32. Number of SUSIs for field theory is less than or equal to 16. All these are famous things. N equals 4 Yang-Mills theory.
But n equals 1 super Yang-Mills in 10D would be an example.
Example of this, and exactly, and that's another example of a field theory in the sense that it is only its massless content has no gravitons. You can, I mean, there is a multiplet, which is just the gauge multiplet with no gravitons. Okay? Oh, n equals 4 super Young-Mills theory has 16 supercharges. Maximally supersymmetric theories have 16 supercharges, roughly for this reason. Okay? Maximally supersymmetric supergravity theories have 32 supercharges. Okay? Now, that's all very well, but how does this have anything to do with dimension? This is the question Shubhan asked in the middle of my long spiel. Okay. So,
32 is equal to 10 over 4.
okay.
11.
Let's choose to work in even dimensions. Okay? Let's choose to work in even dimensions. Now, suppose we're in D is equal to 2m space-time dimensions. Supersymmetries are spinors. Okay? So they have 2 to the power m components. Okay? Whether or not, we can always choose these spinors to be chiral because we're an even dimension. So we can try to look for an example, a supersymmetry algebra with only chiral spinors. If we do that, we are able to come down to 2 to the power m minus 1. Now in some dimensions, chiral spinors have to be complex. In some dimensions, they are allowed to be real. I'm not going to go through the dimension by dimension.
Also Majorana while
That's
sometime.
while is this.
Yes.
So once you made it complex, you can always choose it to be while. That you can always do. But whether you can also choose it to be real is the question of whether you can choose Majorana while. Okay? Let's suppose we're in that dimension where we can do the best that we can. It will turn out the boundary dimension is such a dimension. 11 is such a dimension. 10, you'll see. I'll in parallel do the analysis for D is equal to 2m plus 1. Okay. Here the number of spinors is also 2 to the power m. But here you cannot choose the chiral condition. So here we have 2 to the power m. Now in each case, let's suppose we're in such a dimension that we can choose the spinors to be real. The spinors to be real here or the while spinors to be real here. Let's suppose that's the case. As you know, this is an intricate question that changes dimension by dimension. But let's suppose that's the case. That's the best possible case, meaning the case with the fewest possible real supersymmetries. Okay, now let's first work out this case. In this case, then we need that 2 to the power m has to be less than equal to 32. If we had to make them complex, we would have made m plus 1, because twice the number. We're assuming that we're in a dimension where we can choose them all to be real. Turns out for the boundary guy you can. Okay, so 2 to the power m is less than equal to 32, which is m is less than equal to 5, which is dimension less than equal to 11. Okay, now let's try here. Okay, here we would get m is less than equal to 6, because m minus 1 is less than equal to 5. So D is less than equal to 12. But it turns out that in 12 dimensions, chiral spinors have to be complex. So 12 doesn't work. Okay, because in that particular example, the actual number is not 32 but 64, because chiral spinors are complex. Okay, on the other hand, so the best possible even dimension does not work. The best possible even dimension is 10. In the case of 10 dimensions, as we will see in great detail, because that's the dimensionality of relevance to superstring theory, it's possible to have Majorana while spinors. Spinors that are both chiral as well as So in the case of 10 dimensions, there are two kinds of supergravity theories. One with 16 supercharges. Because you see, in that case, m was 5. So 2 to the power m minus 1 was 2 to the power 4, so 16. You could have a theory where the supermultiplet had only 16 supercharges. Or you could have a theory with the supermultiplet had 32 supercharges. Okay? So you will see that the type 2 theories are theories which have 32 supercharges in 10 dimensions. The type 1 and the heterotic theories are theories which have 16 supercharges in 10 dimensions. So 16 is the smallest number of supercharges you can have in 10 dimensions. 10 dimensions you can also have 32. Okay, you can keep going. But if you increase it more, you won't have a supergravity theory. Right? And the largest dimension in which you can have any supergravity theory whatsoever is d is equal to 11. Is this clear? Is the final set of conclusions clear? I may not have summarized it very clearly. Please tell me if there's something that's not clear. Okay, I'll just say the summary again. Quantum field theory sounds like it cannot exist in higher than 6 dimensions. Actually, there's a cleaner version of this theorem. There exists no superconformal algebras in d greater than equal to 6. Since all quantum field theories are defined by renormalization group flows away from superconformal algebras, that's really a very clean theorem. This is not that clean because we're assuming that there is some way of making it free particles. That there's particle-like representation. You know, in conformal field theories, particles are dubious things. Anyway, it suggests that d equals 6 is the highest number for field theories, and it's true. Okay? For gravity, it's clean because every gravitational theory is free at low energies. Because Newton's constant, the gravitational interaction goes to 0 at low energies. Irrelevant. GMM by r square. Right? If m goes to 0, there's no interaction. The strength of the interaction is proportional to energy. Okay? So in gravity theory, the conclusion was that the largest number of dimensions in which you can have a supergravity theory is 11. In the particular case of 10 dimensions, which is below 11, you can have two kinds of supergravity theories. One with 16 supercharges, one with 32 supercharges. In 11 dimensions, you have to have theories with only 32 supercharges because the spin-Oriel representation has the basic spinor representation has 32 supercharges. Okay? So because of this basic kinematical framework, if you are interested in studying supergravity theories, there is clearly one theory that seems like, you know, the parent of all theories.
Mother.
The mother of all. It's the supergravity theory in 11 dimensions. Clearly it's, you know, somehow the one we should first look at, so let's look at it. All good? Okay. So now supergravity people have gone through this careful exercise of constructing all possible supergravity Lagrangians. What does it mean? It means a Lagrangian that implements some local transformation which, you know, if you freeze infinity becomes global supersymmetry at infinity. That's some local transformation, just like diffeomorphisms are local. Local supersymmetry with an algebra like diffeomorphisms, but a local version of diffeomorphisms plus supersymmetry, that is a symmetry of the theory non-linearly. This is the kind of thing you cannot do with these high spins. Okay, but it's the kind of thing you can do with supersymmetry, with spin 2, and you know, in the 1980s, there was a huge amount of work just constructing all possible supergravity theories. Okay, and in particular, in d equals 11, there is a unique supergravity theory. Okay, and I'm going to tell you about it. We're not going to go through the construction; it's a hard work. Okay, but once they proved that there's one, they've told us what it is, we will use it. Okay, So I'm going to write down first, what is the field content of the theory? Okay. The field content of the theory is the metric. And the field content is a three-form gauge potential.
This is the bosonic part.
The bosonic part. Right. And there's going to be as many fermions. Okay. So I've already told you what the field content is. But suppose you guys are skeptical
And
people.
this is the on-shell, there's no off-shell multiplet.
No. We'll never talk off-shell. Off-shell is very complicated. Yeah. This is just the physical particles. Right. Okay, good. I just told you what the bosonic field content is. But suppose you guys are skeptical and you want to check me somehow. Well, how would you check? Well, we already know enough for you to check. How's that? We know the total number of states that should exist. How do we know that? Well, remember I said we were going to have 32 supercharges, of which 16 are going to be active. And these 16 will form a Clifford algebra with 2 to the power 8 states, because there will be 8 creation, 8 annihilation. Okay, so the total number of states should be 2 to the power 8, which is equal to 256. But in any supersymmetric theory, there are as many fermions as bosons. So the total number of bosonic states should be 128 boson and 128 fermion. Let me check that the number of bosonic states is working out right. Okay, first let's count the number of states inside G mu nu. Remember, we have to count in SOD minus 2. Because the physical state content of the particle is in SOD minus 2. The rest is jazz. Right? Or from the point of view of the counting, that's how we thought. So what representation of SOD minus 2 is G mu nu?
D into D minus 3 over 2. I mean,
What?
in the D dimensions.
So I think what you meant was D minus 2 into D minus 1 by 2 minus 1.
Yes. D into D minus 3 by 2.
D minus 1 by 2. Yeah, it's a symmetric tensor. It's a this two-dimensional symmetric tensor. It's an m-dimensional symmetric tensor. It's m into m plus 1 by 2.
Yeah, no, in four dimensions, that's. Is that
Wait, minus 1.
okay, yeah.
Because you have to remove the trace.
I see, okay. Okay, then it becomes.
If you want the number of traceless. Okay, let's check in D equals 4. In D equals 4, we'll get 2 into 1 by 2.
2 into 3 by 2.
2 into 3, thank you. 3 by 2 minus 1, just 2, which is good. Okay. Let's check this now. So we're in 11 dimensions.
Yeah.
So this is 10, no, this is 9 into 10 by 2, so 45 minus 1, so 44, good. So we've got gravitons is equal to 44. Okay, and what about A mu nu? Well, this is an antisymmetric 3 tensor.
Is it the polarized number of,
Number of distinct
number of distinct
polarizations, exactly. For A mu nu, what do we have? Well, here we've got an antisymmetric 3 tensor. So one way of thinking of this problem is you put 2 crosses. And maybe it's just simple, right? Isn't it just 8 choose 3?
Yeah, 8 choose yes.
Yeah. Let me just make sure.
No, 9 choose 3.
I think if it's give me a minute. Well, yeah, I think basically one way of thinking of this is this. You choose the first one 8 times. There are 8 possibilities.
Yes.
Then you're not allowed to repeat. So you get 7. Then you're not allowed to repeat, so you get 6. But Which order you did it in was up to you. So there's a 3 factorial there.
Yeah.
Okay, so I think that is 8 into 7 into 6 divided by 6 divided by 3 factorial.
That's 56.
That's 56. Are we doing well? No. Have I counted wrong? Firstly, have I said it wrong?
This is totally antisymmetric tensor.
Totally antisymmetric tensor. Have I got it wrong, the number?
I think, sorry, it should be 9 into 8 into 7, right? Because 11 minus 2 is...
You're right, you're right. Why was I was doing the 10 dimensions. Sorry. Yeah, thank you. 9 into 8 into 7 by 6. So that's into 3 by times 2. So that's 3, 4, thank you. Okay, so that is now 12, 7,
84.
84. Oh, good, looks
Precisely
good.
correct.
84 from mu nu. Okay, so we get 128. Right, so it makes up the right number of bosonic degrees of freedom. And what about the fermions? What are we going to get with the fermions? Well, what representation will the fermion be in? Okay, you see, in supergravity theories, more or less by definition, you always have supergravity fermions in what is called the Rarita-Schwinger representation. So what is the Rarita-Schwinger representation? The Rarita-Schwinger representation is a representation with a vector and a spinor index. But, so it's basically the tensor product of vector and spinor.
The spinor part gets thrown out.
Exactly. Except that this tensor product has 2 representations. How do you see that? You see that by contracting this with gamma. When you contract with gamma, you're left behind with a spinor. That is covariant by itself. So the part such that this is equal to 0 defines a Rarita-Schwinger equation, spinor. The part that is purely spin 3/2 doesn't have as Upmanyu said, doesn't have a spin half admixture. Okay, so how do we count the number of particles there? Well, that's easy. Let's just count the total number of particles in the product of a spinor and a vector and subtract the number of particles in a spinor. Okay, so the number of particles in the vector was 9. Remember, we had an SOD minus 2. The number of particles in a spinor, an SO9 spinor, was 2 to the power 4, so 16. Times 16. Okay, and then we're throwing away one spinor index, one spinor. So that becomes minus 16, which is equal to 8 times 16, which is equal to 120. Okay, so the fermionic content of this is gamma mu alpha is Rarita-Schwinger, meaning with the obeying that Rarita-Schwinger condition. Okay, already this counting makes it very plausible that this is going to be the state content of the fields in D is equal to 11 supergravity. Okay, fantastic. So let's move on. Now that we know what the field content is, we need the Lagrangian. I'm just going to write down the bosonic part of the Lagrangian. I don't know if you remember, but there was this time when the Maharishi was putting out advertisements saying that supergravity was the theory of everything. He had the Lagrangian of 11-dimensional supergravity, but he never wrote the fermions. So it's wise not to write the fermions because it won't fit on your T-shirt. Okay. Okay. So we'll follow his example and we'll write the bosons. Okay. So of course the bosonic part of the Lagrangian is square root G R. Good old Einstein. No messing around with that. Okay. Now we've got this antisymmetric 3 form. As we've discussed when we discussed B mu nu with the in string theory, these theories, to make sense, need to have a gauge invariance. Why do they need to have a gauge invariance, somebody? Why is the theory with just just the massless guy, just some Maxwell, some just d of A, the whole thing squared. I mean d meaning d mu without any antisymmetric combination. Why isn't that meaningful? Why does a massless theory, a theory of massless A's, necessarily have to have a gauge symmetry? What? To was unphysical, but what tells you what's unphysical?
There will be negative norms.
Exactly. The problem is that you have harmonic oscillators involving A0 with odd numbers of A0s. In this case, only one A0 because it's antisymmetric. And those harmonic oscillators, if you try to quantize them in a way that is Lorentz invariant, will always have negative norm states just because the guys with AI, J, K have positive norm states, positive norms. Okay? This is an exercise I'm sure you've gone through for Maxwell theory, right? This is the same exercise.
Always choose the Coulomb-like gauge too.
Exactly. You need as many degrees of freedom as there were A0 type. You need as many gauge symmetries. At least as many gauge symmetries as there were A0 type oscillators to be able to get rid of these states. Okay? But those are basically like some 2-index kind of gauge invariance. Okay? So the theory we look at will have invariance under A mu nu, just exact analog. Let me write it in form notation. A goes to A plus D chi. Well, this is a 3 form and this is a 2 form. Okay, this will be the gauge invariance of this theory. Therefore, we won't have actions involving A alone. Or almost not. We will, but not in the most straightforward way. The action will most easily involve dA, which we'll call F. This is a 4 form. And then what we will have is F and then star F. Right? Oh, maybe I'll just now write F mu alpha beta. Beta and integrated. Where this F was this object. Notice that we're trying to write down 2 derivative actions. Okay? Notice we're trying to write down 2 derivative actions. Einstein-Lagrangian is 2 derivative. This is 2 derivative, that's great. Because each F has 1 derivative. Now can we do anything else at 2 derivative order? Can anyone think of an additional term you can write down at 2 derivative order? Other than those that we've just written down. Amio, any suggestions? Related to a theory you've studied.
Something like John Simon's A wedge, F wedge, F wedge.
Exactly. A wedge F wedge F.
Yeah.
This is 2 derivatives because A is 0 derivatives. Each of the F's is 1 derivative. And it's an 11 form because F is a 4 form. So 4 plus 4, 8 plus 3, 11. This can be written down. Doesn't look gauge invariant because under gauge transformations, this is gauge invariant, this is gauge invariant, this goes to D chi. But now integrate by parts. The fact that D of F is 0 because of Bianchi identity. Why is D of F 0? Just because D squared of anything is 0. Means that if you integrate by parts, this thing is 0. So it's not locally gauge invariant, it's gauge invariant once you integrate. Okay, this is the hallmark of Chern-Simons terms. Okay, so the most general 2 derivative term you can write down in your action is some linear combination of these. Now what is the information At this level, what is the information in this action? Actually, very little. You see, we choose a metric. Now, nobody's told us what the overall normalization of f is. So we can always choose the normalization of f so that the relative term here is 1, though I think Polchinski chooses minus half.
Yeah.
We can choose whatever normalization we want. Okay? And then, however, once we've done that, we're stuck now with this term. It's whatever it is. We can't change the normalization of A again, because if we do, we change the relative normalization between G and... We don't want to change the normalization of G, because G is 1 at infinity, let's say.
So there's, even in front of those terms, we cannot write any other coupling terms, right?
Yeah, so just at this level, you could have written whatever you wanted.
Right. I mean, but supersymmetry...
But supersymmetry is going to fix it. Okay, so there's one term here that you cannot guess without doing work.
Will not multiply the last term, right?
Root G will not multiply the last number, you're correct. Okay, square root minus 3 if you want to be precise, and that's it. Okay, so the only information that we needed to take from those guys, apart from the existence of such a theory, was this one term here. The rest, there weren't too many choices. Okay, that there exists a two-derivative theory that works is great. It's far from algebraically, these are totally amazing things. You know, all these supergravity people from the end of the 1970s to beginning of the 1990s carefully worked out all these theories, utterly unappreciated. In the sense that other than the supergravity people, nobody cared about what they were doing, including the string theorists. Remember this talk by Polchinski in which he said, you know, he was talking about after all come together, and he was saying, string theorists just completely ignored the supergravity people. Then he paused and said, and we were right to do so. I mean, his point was there was no indication then that it was connected. But you know, these people have done this really hard work. It's totally crucial, and often the way we meaning the string theorists make progress is by skimming the cream. Some great stuff other people have done. Take it on. It's really underappreciated. The people who did this, these calculations go over months and months and months and months. And you know, 5 years later you have 5 citations. I mean, but it's key to much progress, you know. Okay, fine. This theory, plus fermions, which we won't write down, defines 11-dimensional supergravity with 32 supercharges. As you can see, it's really a simple thing. You know, it's not much more complicated than gravity theory by itself. Is this clear? Okay, so this is the first theory which, at the moment, I'm going to present it like an organizing principle.
We see very easily that it's Suzy.
That we cannot see from here.
Yeah.
Okay, see, there are some indications already. The first indication is that the number of degrees of freedom is matching. And you can try to write down putative supergravity, supersymmetry transformation rules at the global level and at the linearized level, and you'll be able to come up with some reasonable looking rules. But that this thing is locally supersymmetrically invariant.
Yeah.
It's a highly non-trivial thing. This is what these guys had to work out. And we can't even begin to see it without the supersymmetries, without the fermions. Yeah.
No, yeah, I understand.
Yeah, it's a highly non-trivial thing. Okay, but it is.
Because it will involve mixing with the fermionic part.
Of course, that's what supersymmetry does, right?
Yes.
Yeah. Sorry, I'll just... Hello? Hi, Shreyans, I'm in the middle of teaching a class. Could you call back in 20 minutes or so? 20 minutes, is that okay? Okay. Okay, excellent. So, for d equals 11 supergravity, this is all that we have. Now, I'm going to use the fact that we know this theory to deduce another theory with 32 supercharges, namely the theory that we get by taking this theory and putting it on a circle. That will be some 10-dimensional theory, which we will call type 2a supergravity. Okay? There will be a 10-dimensional theory which we will call type 2a supergravity, which we will be able to completely understand from this starting point.
So how can one get the type 2b supergravity from here?
Well, in string theory you can T-dualize.
Okay.
So there is a way of getting it, but it's not completely obvious.
I see. No, I mean, so the procedure is to get type 2 supergravity from 11D supergravity and then
T-dualize, which is equivalent to taking M theory on a 2 torus, keeping the ratio of the sizes of the 2 torus fixed, and taking the size to 0.
I see. Okay.
But the problem with that point of view is that some of the degrees of freedom that make the 10-dimensional fields come from wrapping two branes. So you don't get it just from supergravity.
I see.
Okay, so it's not some simple thing. Another way of saying that is that type 2b theory is chiral.
Huh.
You never get chiral theories by starting from some higher dimensional theory and compactifying.
Right.
Unless you start with a chiral theory. And there's no chirality. Yeah. So it won't be so easy to get it.
I see.
You have to do something special. Okay? Right. So, but let's first focus on type 2a supergravity. Okay? So, let's see. So, what we've got now, okay, first let's do some basic counting. What fields are we going to get? Well, each of these fields is going to give rise to its daughter fields. So, the metric will give rise to what?
One scalar, 10 gauge bosons, and
Excellent. It will give rise to a metric, a scalar, and a gauge boson. How do we see this?
one gauge boson, sorry. There will be 10 components.
Yes. How do we see this? One crude way of seeing it is, of course, this is just decomposition of a symmetric traceless 2 tensor of SO9 into representations of SO8. Okay, so we've got the symmetric 2 tensor which I've drawn by this matrix. And now we're breaking it up so that this is the special index. So whatever's here is symmetric 2 tensor, and let's say that we choose this. The whole thing was traceless. So the trace in here or this scalar field or either one can be chosen as 1 degree of freedom. Let's choose this guy. So whatever the trace part is here, it's not a degree of freedom. There's one scalar and a symmetric 2 tensor. It's the scalar, symmetric 2 tensor. And then what's left is a vector. Not two vectors because it was symmetric. So whatever was here was the same as what was here. Okay, so you've broken up into, this breaks up into this. And just as a sanity check, let's do the counting. So this we had nicely counted was 44. Here we'll count again, we'll get 8 into 9 by 2, which was 36 minus 1. So 35. 1, and here this is 8. And that adds up to 44. Okay, so that's how the metric breaks up. Then we have this 3 form.
So it's a 3 form and a 2 form.
Excellent. Into a 3 form. Because this index here could either be a special direction or not. Because it's symmetric, you can't have two of them being the special direction. So if
we started with 11 dimensions and we are compactifying along
one circle.
one circle. So,
But remember, we're always doing little group analysis.
oh, I see. Okay. Yeah.
Okay? Right, so that's why this was 8 into 9 by 2.
Yeah.
right? Okay, so now what about this guy? This guy is a 3 tensor and a 2 tensor because either there's a 0 index or there's not. If there's no 0 index, then we've got a 3 tensor with the remaining SO8 indices. And if there's one of them, then we've got a 2 tensor with the remaining SO8 indices.
The first term would have 56 components.
The first term, that's what we computed, right?
Yes.
So this was 56. And this is 8 into 7 by 2.
28.
So that's 28 components. 28, and does that add up to 84? It does. Good. So good. So a full field content is G mu nu, a scalar, a vector, a 2 tensor, and a 3 tensor. Now this, of course, is not called 2A supergravity for no reason. It's because it's the, well, I mean, it's more like 2A. String theory was not called 2A string theory for no reason. It's the string theory that reduces low energies to 2A supergravity. And now we see all the familiar fields of string, all the familiar bosonic fields of string theory coming out. Okay, there's the metric, there's the dilaton, there's the B mu nu field. These are the NS sector fields. And then we also have the Ramond sector fields. The Ramond sector fields, if you remember, were either all odd forms or all even forms. And you don't go beyond 4 indices because then you can self-dualize, right? So in this dimension you had all, 2A had all odd forms, and that was the A mu and the C mu nu. 2B will have another 2 form, and then we'll have a self-dual 4 form. We'll see that as well. Okay, so we've hit upon the field content of type 2A theory. Now we need to analyze the action. Okay? Now, in order to do that, it's very useful to choose the right. So we're going to start from here.
Einstein frame.
Yeah, it's very useful to choose the right way of writing everything. So let's choose it right. Okay, all this is good, right? First, the metric. There's a class, so. You have a class? You need the room? Yes, okay, I'll stop. Yeah, thank you. Okay. Okay, metric, we'll do that next class. Okay.